So our functional is not only this integral plus, but the integral plus this, yeah, and this is identical to the value. To the value to this value, and this compensates. Yeah. So okay, here is the integral only without the final value here. If we add this, the final value, yeah, then this vanishes in the sum. So then we have that our our original functional with end value equals only the initial term plus an integral of this v, which is remaining. So this vrv term. So, but if we choose the u such that the v becomes 0, yeah. If we choose the u such that the v becomes 0, we have no integral anymore. Yeah, and we have only the initial value remaining here. But what can we see from this formula? Yeah, that indeed, if we set this v to 0, then we get the minimum value of the functional. Yeah, because this is non-negative. So, and the minimum value then is this expression here. So, okay, and this is then yeah, our our optimum. So what do we have to do? We have to set the u as equal to fx, and this is f is this, and x has to satisfy this differential equation with the initial addition, initial condition. So yeah, and this is then the solution of the problem. The only thing remaining is, does the solution of this Riccati end value problem exists? It exists at least for small times, yeah, because it's an ordinary differential equation. We have an initial, now in this case, final value. Then the solution exists at least in a small time interval around the final time t. So, but yeah, how large can this interval be? And we don't know. So we just have to compute the solution of the Riccati differential equation, and at some time it will tend to infinity. Yeah? And okay, before I discuss this, yeah, let me say there is a theorem which says, okay, this problem indeed has only a minimum, or is bounded below, as long as the solution of the differential equation exists. Yeah? So so if this time interval is so large that within this interval the solution of the Riccati equation, which starts at the end time, at the final time, tends to infinity, then indeed this this problem has no solution. So there is no infimum. Yeah. Okay, I will not go into the details here. Yeah, you can read the details in this nice book of Bell and Jacobson, a very old book on singular optimal control. There the full proof is given that indeed, so if the solution of the Riccati equation escapes to infinity, so there is no solution of the minimization problem. Okay. So let's come back to this. We now know how to solve this minimization problem if there's no end constraint, but we can introduce the end constraint again. So now I take here matrix C instead of the psi, because this relates then to some information on former slides. So now we want to have that final time we have the given value for C of the final state. So okay, it's now there comes a complicated formulation, but okay, let me come back to this general formulation. So so the structure of our cost functional is now this. So, and now we would like to meet an end constraint, but this is what we already had some lectures ago, namely when we introduced controllability. There we had the case we had to meet an end condition. So, and we found a formula for the control which achieves this, and this control also minimizes something, and we found out it minimizes an integral of this form. So in the slides about controllability, it was r to the -1, so the inverse of r here in the middle, but we can just replace the inverse of r with r, and then we know how to minimize this integral via and simultaneously achieve the end condition. So and how did we do this? With a feedback which was given by the controllability gradient. And we just can do this here in this case too. So so we are back with controllability. We choose the right controllability gradient with the right weight matrix and get an additional feedback. So which then minimizes our problem with end constraint. That's all. So maybe I don't have to go into this. So here's the controllability gradient again with C and C star on the left and the right. Okay, I don't go through this slides in detail. So and now in all the computations so far, we always assumed that the matrix R is non-singular. So we needed this in both approaches, that the approach with a Lagrangian multiplier and also in the approach with addition of a differential, because in the first approach we needed it in order to eliminate the algebraic equation from the differential algebraic equation, and in the second approach we needed it for the Schur complement. So the Schur complement needs that the lower right block is invertible, because the Schur complement contains the inverse of that block. Okay, but what happens if our matrix R is singular? This is a new problem now, and here's a very simple example. Suppose R is completely 0. And consider this cost functional here. So in here, indeed, we have no R block. We have only an identity block. So our cost functional is just the integral of this squared norm of x. So of course this is bounded below. So there is an infimum, but is there also a minimum? Okay, we need an additional differential equation. I just took this one, but does not matter what you take. So the only thing which is important in this case is that the A and the B matrix which you take here form a controllable pair. So in this case we have the A matrix is minus identity and the B matrix is the identity, and this is clearly controllable. So why do I need controllability for this case? It's because this should be an example for the fact that there can be an infimum but no minimum. Yeah? And if you have a controllable pair and you consider your time interval, okay, 0 is here and final time is here, and you have an initial x0. Yeah? So, and by controllability, you can fix a point here, yeah, and control the state. So this is the state. You can control the state immediately to 0. So in a very small time interval, and this does not cost anything because your cost functional does not contain u. Yeah? So it contains only x. But if you have a very small interval here, yeah, okay, I should say, if you have controlled it here to 0, then you can, in this remaining interval, you can set the control to 0, because we have a linear differential equation, and if our initial condition is 0, so our state remains at 0, and we need no control for this. Okay, you can say, okay, this is in the ideal world. If the matrix A is unstable, it will will leave the 0 position, but then you need only small controls to keep it there. Okay, but in the ideal world, so if the x is at 0, it remains there. Yeah? Okay, so so the state trajectory is indeed then this. So, but you can make it the time interval arbitrarily small. Yeah? So you can make the integral arbitrarily small, but you can never achieve 0. Yeah? You can make it very, very small, but you cannot make it 0 because it measures the size of the x. Yeah? And there is always some x because you start with a non-zero state. So the infimum exists, but there's no minimum. Yeah? Okay. Okay, this was the motivation for some researchers to, in order to can say that there is a minimum, to consider impulses, so distributional controls, yeah, which set this state immediately to 0. So then you have to extend the theory and introduce new objects. Yeah, yeah. The distributions. So there is no minimum. So this is one problem, and here's another problem. Here's a case where the infimum is minus infinity, so it's, the functional is not bounded below. So I take identity here, then the integral is indeed this 2 times real part of this inner product. Take any differential equation. So so the J can be made arbitrarily large and negative because here you have this inner product, and you can choose just u as minus x. So for instance, yeah, so minus 10,000 times x. Minimize. Okay, this greater equal 0. This is remaining for copy and paste from the first from the slide before. Sorry, I will remove it. Yeah? This can be arbitrarily negative, so there is no minimum. So, and when I made this slide, I the question came to me, is this functional bounded below if we add an n constraint? Because then we cannot choose the u freely. Yeah, this is a homework for you. So now, up to now, I discussed only the finite horizon case. That means the capital T is a finite number. Yeah, but now we turn to the infinite case. So there we have only this integral, no end value, because it makes no sense. Yeah, we could introduce this, but then we have to add new constraints on x and u. So, okay, and we are now interested only in trajectories which tend to infinity as x tends to infinity. Okay, so let's say x and u, they are square integrable. We have an initial value, we have the differential equation. Yeah, and so x and u should be in L2 of the interval 0 to infinity, and yeah, this means that these integrals are finite. So, and in the coming derivation, I always assume that A and B are a completely controllable pair. So because this then guarantees that for each initial value there are indeed trajectories for which x tends to 0 as t tends to infinity, and it's just because of this. If there is A, B is controllable, and I start, it's precisely this. I start with an initial value. I can bring it to 0, and then I can set the control to 0, and my state remains at 0. So so and now I introduce a notation here. It's this v plus of x0. In general, there's also a v minus, but I will not discuss this here. I have not enough time to do this. But I need an initial index here in order to have a difference to other v's, which I will speak about. So, and this is just defined as the infimum of our cost functional. Here, comma should be. So, where x and u satisfy our conditions, constraints here. So, and now we make the assumption that the infimum is finite for all initial x0. And here is something mysterious, namely that then there exists a matrix, a Hermitian matrix P plus, so that this infimum can be computed in this way by multiplying the initial vector from the left and the right with this P plus. So why? And you find this very often in control theory literature. So so people are a bit sketchy there. They just say, okay, because this is a quadratic functional, so, and we minimize it with respect to a constraint. So there must be a matrix so that the minimum can be computed, or the infimum can be computed via this formula. There is such a matrix. Yeah? So, and indeed, oh, now I have to go back some slides, but okay, now I just can say on the slides before there is a proof sketch for this. Oh, okay, no, I have to say more. Oh, yeah. So here constraint minimization quadratic dependence of infimum on constraint. So suppose we have a quadratic form defined over a vector space, and we consider here again a linear function, and here's the right hand side, the value of the constraint. So, and of course we get an infimum dependent on Z. So, and so here's a proposition. Let S be a subspace of the space of all possible right-hand side Z's, such that the infimum is finite for all Z in this subspace. And the statement is then that the V of Z is a quadratic form. That means here is a bilinear form. So, so where you can plug in the Z twice, so you get a quadratic form such that this equation holds. Yeah. So, and if Y and the subspace S are vector spaces over the complex numbers, then yes, we indeed have this. So if Z is a vector, then we can write this as Hermitian form. So then this pi can be chosen as as sesquilinear form. So, and I only give you the proof idea because the details of the proof are not difficult, but you have to calculate a bit. Yeah, and so, and the basic idea is that this infimum satisfies the parallelogram identity. Yeah? And whenever we have a function which satisfies the parallelogram identity and is also has some additional continuity property, then it's indeed a quadratic form. Yeah? So, what does parallelogram identity mean? Suppose we have some function q, then it satisfies then the parallelogram identity is just this here. So you plug in the sum of two vectors twice and the difference and add, then this right hand side comes out. This is the identity. And for the proof that this Q is then indeed a quadratic form, you need some continuity. But it's a bit surprising. You need this continuity condition. You do not need it if you work only over the rational numbers. So then, over the rational numbers, the bilinearity follows only via the parallelogram identity. So, so, and from this identity you can find your pi function in this way. So, and this is then real bilinear. So, but if you want to have it complex bilinear or sesquilinear, linear in one entry and anti-linear in the other one, you have to define the pi function in this way. So, and okay, and this proposition is then proven in that way that you first verify that this V of Z satisfies the parallelogram identity and this continuity property, and then everything is done. Okay. So where did we end it with? Okay. So the P plus exists then. So, and we now would like to draw conclusions from this fact. So, back to our matrix in the cost functional and the additional differential. Yeah, and we would like now to find not a matrix function P, we want to find a constant matrix P. So no P dot is involved here anymore. We would like to find it. But suppose we have it. Yeah? Suppose we have found such a P. So then the whole sum here is non-negative or positive semi-definite. And then we can make a full rank factorization of this Hermitian non-negative Hermitian matrix. And we can then write this matrix as some matrix of rows and the conjugate transpose of it. And so this splitting in K and L corresponds to the blocks here. And the number of rows in this matrix equals then the rank of our matrix F of P. So, okay. This can be done if we have found a P, a P which is non-negative. So, okay. But now, if we have made this, so we can equate everything in this product with the blocks here. So, and then, so we have, what do we have in the upper left block of this factorization? We have K star times K. This is if we multiply everything out. We have K star times K. So what do we have in the upper left block here? We have Q plus A star P plus P A. So this is this. And here we have the block in the factorization. And so the same with the other blocks. In particular, with the lower right block here, 0 plus R. So we have an R in the lower right block. This is then L star L. And these equations are called the Fourier equations by this Russian mathematician. And so in the books on control theory, the problem of finding a P such that this sum becomes non-negative, semi-definite, is often stated in this form. Try to solve the Fourier equations. Try to solve these equations. That means find the P, the K, and the L. So, why should we look for the K and the L? Because then we can write our cost functional in this nice way, namely. So here again we add this differential and subtract it. So we have the F of P here in the middle. And now we can replace this F of P with this matrix product. And we have to multiply, if we put it here, we have to multiply the XU with K and L, and all the same from the other side, and out comes the square of the norm of Kx plus Lu. So this is then this integral. So, and we have the boundary terms. And then we can think further about the boundary terms. We have a nice expression for this. And now we see what we have to do in order to make this part at least 0. Yes, we have to satisfy this equation. So there has to be a connection between the u and the x. What I should say is at first sight it seems that the k has the same dimension as this block, but it does not need to have. So this matrix can have long columns. Indeed, in the extreme case, the columns have the length of this whole matrix here. So this K and L may be rectangular matrices. So it depends on the rank of this here. So the rank is indeed the number of rows. So the number of rows is the rank, and yes. So you have to look on this as a multiplication in general with rectangular matrices, with a lot of rows. So so we end up with this. So if we can find a P here, then we have this nice identity. So, and this is a dissipation inequality. So what does dissipation inequality mean? So dissipation inequality means you have two kinds of functions. You have a storage function and a supply function. And the storage function only depends on the state, and the supply function also depends on the control. So, and let's say, so we have a storage function. This has a value depending on the state at, let's say, the final time. And this should always be less equal than the value of the storage function at the initial time. Let's say, okay, t0, so t0 is smaller than t, plus this integral from t0 to capital T of the supply function x and u dt. So, and this storage function is interpreted as something like energy, which is stored in the system. So this is the energy at final time. That is the energy at initial time. So, and this is the energy supplied to the system. Yeah, and because there is a dissipation of energy, we don't have an equation here, but an inequality. So there's a energy loss. So, and of course you can write it in this way. Okay, then you have an equivalent inequality, and look now here at the expression. So you have the inequality the other way around. You have greater equal instead of less equal. So if this should be interpreted as storage and supply function, you have to take a minus everywhere, and then you get the right inequality. Okay. Now, okay, we derived the upper equation here. Now take limits, set the t0, the initial time, to 0. So of course then we get here 0 here. And suppose now that our state tends to 0 as t tends to infinity, then this final value is not there anymore. So then we have only this. So, that means that the value of our function is greater equal than this expression. Multiply the p with the initial value of your state. So, okay, our assumption was that we can have such an expression, which is the case if this f of p is non-negative for some p, the p we look at, then our conclusion is that that then obviously our functional is at least bounded below. We don't know whether it has indeed a minimum if the infimum is attained, but at least the infimum is not minus infinity. Functional is bounded below for all x which tend to 0. So this is an immediate consequence on this. But now, so this expression is a lower bound, but we have our p plus, which is assumed to be to give the greatest lower bound. So each p which satisfies this inequality has to be less equal than the p plus. So we conclude that the p plus is the maximal element of all possible p's. So if p plus exists, so we have a finite lower bound, then p plus is the maximum possible p of all these p's, which makes this sum make this sum non-negative. Okay. Let me see. Okay. So yes. So there's okay. Moment. Let's come back here. What do we have? Okay. Point 4 has to be discussed. So okay, let's look at this inequality again. So we can achieve the if K and L are such that L is a square matrix. If L is a square matrix, then we can choose as U, so minus inverse of L times K times X, and then this integral becomes 0. So, and then the J attains the lower bound here. So the minimum of J is then indeed this, provided that our choice of the U is stabilizing. So if we can choose U in this way, because L is non-singular, it's a square matrix and non-singular, and if with this control the associated state goes to 0 as t goes to infinity, then we don't have this term, and also this integral is 0, and we arrive at the smallest possible value which this can have. So then the optimum is found, and then the p must be our p plus. So yes. And now let's come back to the Riccati inequality. So if R is positive definite, so we can again apply the Schur complement, and we are now in the general case. So sorry. We apply the Schur complement, and we see when we apply it, then here the upper block disappears, and okay, well, if we apply it, the Riccati term appears here. So, and the whole thing is non-negative if and only if the Riccati term is non-negative. That means our f of p is non-negative definite if and only if the Riccati term is non-negative definite. So whenever p satisfies this Riccati inequality, then it makes the f of p non-negative. And then we can factor it into the f of p. We can then factor into two parts. So the lower part here, okay, this is then the k part, and this is the L part. So here's the minus is missing. This is the k part, and this is the L part of the full rank factorization. And in the best case, so the lower row, the upper row is not there anymore. So the K0 here is the empty matrix, and this happens if and only if P indeed satisfies the Riccati equation. So if the here you see the statement: if the Riccati equation is satisfied by P, then indeed we are back to things we already discussed. Then we can set U equals K times L to the minus 1. So and this is done just this expression here. So okay. So I told you about this, okay, this non-negativity of this sum here, and okay, but I did not drop the term LMI. So LMI means linear matrix inequality. This inequality is called linear matrix inequality. Inequality with respect to the Hermitian order. This is greater equal 0 in the sense of Hermitian matrices. So, and it's linear because, okay, it's linear in P here, plus a constant term. So, so suppose this is satisfied, then we have this dissipation inequality. So, but suppose now we are the other way around. We know this dissipation inequality holds. So, and then we can conclude that the LMI holds, the linear matrix inequality. So, and this is just by taking the linear matrix inequality and differentiating it. So, okay, what do we have? So we have this right-hand side, and we have this inequality, and this right-hand side can now again be replaced by this integral. So, and we can move it to the left-hand side again. So, and then we get this expression. So, and consider this as a function of t. It is 0 if t equals t0 and is greater equal 0 for larger t's, and it's differentiable. And yes, and then so the differential at 0 must be non-negative. So then we end up with with this. Okay. And now on this slide, I tell you that the minimization problem which we have does not depend on initial time. So I introduce everything by saying, okay, we start at time 0 and look at the time from 0 to infinity. But because everything is time invariant here, we can start at any time. Of course, makes no difference whether we consider here trajectories which start at 0 or trajectories which start at an earlier time or a later time. So, okay. This is just for the following, because now we have to move the starting time around a bit. Oh yeah, now things become a bit technical. So because what I would like to show is that our P plus, which is only defined to be the infimum, or method to the matrix with which we can compute the infimum, it had, from the definition, it had no special properties. Yeah? But I would like now to show that the existence of this matrix, yeah, already implies that this matrix satisfies the dissipation inequality and the LMI. And this is a bit involved. So let me see. It's rather late here. Should I really go to this through this in all details? Okay, let me just look what comes. Okay, I have to do this, unfortunately. So, okay. So now we start at the time t1. Yeah. So and we consider our integral, and it so there must be a control and an associated state. So this that this is a bit smaller than the infimum. So if we take the infimum here, and we start at x1, if we take the infimum here and add a small epsilon, there must be a control and a state so that this inequality holds, because that's the definition of the infimum. So if we increase the infimum a bit, so we have no lower bound anymore, so there must be a value smaller than this. So now take a smaller time than this t1. So by controllability, there exists a trajectory which then connects the instances t0, x0 and t1, x1. So, and we now can define a new trajectory built from our old trajectory and the additional one and the old control and the initial control. So, and then we have this, that the v plus of x0 is by definition of v plus less equal than this integral of this for this new trajectory, and this splits into two parts. Yeah, so the first added part and the part we already had. So, and this is then an integral starting from we keep this, and we bound this by v of x1 plus epsilon. So now we can do this for any epsilon. So, and what do we have then? We have a dissipation inequality for the v. So the v is then the storage function, and our integral. So the integrand here is the supply function. So, okay, but the v plus here is given by our matrix P plus, and the same here on this end. So our P plus satisfies the dissipation inequality. Yeah, and that means it also satisfies the LMI, because every matrix P which satisfies the dissipation inequality satisfies the LMI. So our P plus is indeed a solution of the LMI. So okay, here I end this lecture with all this synopsis here. So all the assumptions, the assumption we made here was that A, B is controllable, because we we needed that there are curves which can be controlled to 0, yeah? And yeah, later on we will need more controllability. So okay, then, so the statement is the linear matrix inequality has a Hermitian solution. This is equivalent to the fact that the infimum here is finite for all initial value, initial states. And so if these two statements hold, then the maximum solution to this linear matrix inequality is indeed the matrix with which we can compute the infimum. So, and if this linear matrix inequality is satisfied for some P, then we can perform this Fourier factorization, and we can write our integral in this nice form, and this is a dissipation inequality up to sign. So, okay, and in the next lecture I will call this LMI, the linear matrix inequality, feasible if and only if it has a solution. So, and the solution may be also the solution of a Riccati equation, but it does not have to be. So this is a more general theory which includes more cases. Okay, so, but my time is over, so I have to stop. Tomorrow I need 2 lectures. Yeah?
So
morning one in the afternoon, and then we will have a questions and answers session. Yeah?
Problem solving session, a questions answer session. So whatever questions you have, you can ask Mika tomorrow.
Yeah. Okay. Okay. Did you make a copy?
Yes, sir, I am. I'm able to find this on software.
Okay. Okay.
দুটো লাগবে ওই জিয়ার সাইডে নেই
কোথায় নিচে লেগে
ছিল তো কে লেগে গেছে। ওইখানে আমি লিখেছি
কালকে আমি মনে করি তুই সকালে ফোন করেছিস
জিয়ার সাইডটা
ইয়া